Thank you, thank you, thank you very much. It's time for the end of the year awards. And here are your class winners. Roll the music. Happy last day of school, everybody, and I just want to shout out a big congratulations to all of you. Whether you were listed in the awards or not, all of you have done a great job. And you might ask me, why, Mr. Nyson, are you wearing sunglasses? Why are you wearing shades today? And the answer is, because I know how bright all of you have become, and I'm just protecting my eyes. And so, but I still know that some of you are still bitter. And you're bitter because you say, I always get in trouble for stuff I didn't do. And it's like, you know what? That's right. You do get in trouble for stuff you didn't do. You didn't do attendance. You get in trouble. You didn't do your homework. You get in trouble. So make sure you get your attendance taken for both days this week. And we do have one more assignment that you have to do today and get it in the night. And if you have any missing assignments or any late assignments, get those in. And then today, get any textbooks, library books, or things turned in at the school from 10 to 1 today. And so pause the video if you have to right now to get the attendance taken. And we'll be back for your last day of e-learning. Store for the last day of geometry. It's hard to believe. If we didn't have this corona thing, I would say you've had me for 540 math classes. And so hopefully you haven't gotten tired of it. I sure haven't. And so I've enjoyed being with all of you each time. And so I kind of will take these off because it's kind of hard to see, but it's hard to believe. And so all of you, whether you were on a certificate or you have participated in math counts, or you didn't like competitions, or you did, but you were busy playing basketball all the time and I could never get you to go. But all of you have done a great job. And so all of you are very smart in math. And so just keep it up and you will soon see how smart and how well prepared you are and how good you are on what you're doing. And so when you get to high school and things, those teachers are going to be excited to have you. And so we've thoroughly enjoyed it. And so thank you, Sidel. This is wonderful. She made this, all these memories on this, the function machine, Notre Dame fight song, the tractor video, Mr. Nyson, not knowing or do know how to pronounce whale and white correctly, function machine, swamp fox, trapezoids. And this has to be one of the easiest tests I've ever given. I took it this morning and didn't miss a one, so I'm sure you'll do fine. And so lots of things. Thank you for that. And also, you know, I would have played some Brady Bunch songs part of these videos, but you can't find the music except for the main theme. And so we have this, and I will gladly display these in the room. And so thank you so much. And those will be hanging up in the classroom for next fall. Okay? So thank you. That was wonderful. And so we used that today. And so what we're going to do today is we're going to finish our graph theory. And so today I need textbooks and I need your mirrors. We got about just over half of them in, almost 2/3. And so that's right, because we got the other third. But I got my list. And we're going to track you down if you don't get it turned in. It's not, well, bring it in the fall. No, 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 no. I'm not waiting. You could fall off the face of the earth, or I could. And so, Mr. Nyson, the world's not flat. It's an expression. You know, math teachers, they like expressions. And so, when you get old, we use strange expressions. But get that stuff turned in. Don't make up your own rules going, oh, I'll just do it later. Get it turned in. And so, everything's due tonight, 11:59 p.m., because midnight's actually tomorrow. And so, and get your attendance taken. But for the last day of geometry, 3 years, here's the last notes, 132. We're going to finish our graph theory discussion. There's things called Euler Paths where you have to drive down every road, and you don't want to drive down the same road twice. And a circuit where you begin where you end. Hamiltonian circuits where I just need to visit every town. Like a business person, I got to go here, 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 and I want to end up back where I started. And what route should I take? And then there's things called minimal spanning trees, which aren't circuits. They don't have to like bridge together. They just fan out, but everything has to be connected. And so today, some of you, it's like, this is my favorite. I just guess around. And so we'll talk about some methods. It is in your book, but you're hopefully turning your book in, unless you want those odd answers quick. Page 682, 1 to 7. And then before you get that turned in. But I have it all here. I have it scanned. I got the pages from the book. And so you're good to go. Okay? And so what we're going to do today, this is notes 132. And sometimes I have it, the problem highlighted lightly, so you can like highlight over it. And the directions, we don't have to have a path and we're not a circuit, because that would be extra routes you don't need. You just want to connect things, and you want to connect them to minimize something. And so maybe I want to connect towns, and this is how much each of these numbers maybe represents how much it costs to build a road. Certain roads are cheaper because I don't have to go over a river. Certain roads are cheaper because I don't have to go over a mountain. If I just go across a field, that's cheap because it's just flat. And so maybe I want to connect town A, B, C, D, E, F, G, H, but I want to connect it in the cheapest way. And so how would I do that? Well, you can take each town and you could just take the cheapest road and then try to connect them. And then we add it up. So what roads would you want to use? What could I do? And so Tim, like connect D and E, and that'd be a 5. This is the Tim method of doing minimal spanning trees. Well, then we'd have to connect either the D or we'd have to connect the E. Well, I could make this a 5, and we're just going to guess around at this. We could highlight some of the smaller numbers. We could say, well, this would be a 7. And then this would be an 8. Maybe I want to connect this. That's the cheapest, 13. What's the quickest way to get to the G? Well, maybe it'd be this 12. And I need to connect the F. Well, connecting the F, that'd be a 10. And then I want to connect that, and that'd be a 9. And so notice we connected all the vertices. We're not talking about a path. We're not talking about tracing with our pencil without picking it up. We're just connecting all the towns. Network in the cheapest way possible. And we want to find it. And so you can just guess around. And if we did it this way, this answer would be 5 plus 9. I should use the highlighter. And so if we add these up, 5 plus 9 plus 10 plus 8 plus 7 plus 12 plus 13. You don't want a circuit. You don't want to add in an extra road. Just connect the beginning to the end. And so if we add these up, 13, 12, 8, 7, 9, 5, and 10, what would we get, Avery? And this homework is not optional. Hee 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 hee. It'd be 64. Now the question is, can we beat that? So maybe you don't need a method. You can just look at it and go, I can connect all these with 64. I minimized it. Well, there's different methods, and these aren't things you memorize. My purpose today is just to show you a whole new world. See right here? Whole new world. And there is a whole new world of graph theory. And some of you are like, I like this. It's my favorite part of math all year. And so if this is what you like, you can go to college and you can become a graph theorist. And you can take a class called graph theory. And so we don't really care too much about whose algorithm this is. Just here's different things people try. And can you beat a 64? Highlight the lowest value from each vertex. Well, the lowest value from B is an 8. The lowest value from A is a 13. The lowest value from G is a 12. The lowest value from C is a 7. The lowest value from H is the 7. The lowest value from D is the 5. The lowest value from E is the 5. The lowest value from F is the 10. And so connect those and then see if this would have given us our 64. And then if you can't get everything connected, then how would you connect that? Well, then how would I connect this? Well, you'd connect it with the 9. And see, we would get our 64. And we used Borowka's algorithm, and guess what? We didn't even know it. We didn't even know it existed. And so that's the technique. Here's Prim's algorithm. Pick an arbitrary point and just connect it to the lowest number. So what number do you want to start with? What would you pick, Carson? You want to start with D? And then just connect it to the lowest number. Well, the lowest number would be a 5. Now connect it to the lowest number. That'd be a 9. Now connect it to the lowest number. That'd be a 7. But see, then the lowest number you didn't use would be the 20. Then the lowest number you didn't use would be the 12. Then the lowest number you didn't use would be the 13. Well, then I never connected the F. Then we connected 10. See, we would almost get it. But see, we didn't quite get this. And so this would not give us, in this case, the lowest one. But in other cases, it would. And so we have a problem here, and we'll see how many times it takes. See if we can get it on the first try, or see if we can get it on the second try. Could we connect all these vertices with the minimum cost? And so you want to scan, and you really want to get the lowest numbers. This 26 and 30, it's like probably building over the Rocky Mountains or something, a railroad track. And so we probably want to connect the 2 and the 3. Then what would we want to do? Damien? Connect this to the 5, because that would get that dot. Now this 4, we would probably want. Now how can I get the other ones? Well, to get to this, Kirsten, yeah, connect the 12, that's good. And then the 16. And that'd probably be the quickest way. And then what would be the cost of this? 5 plus 2 plus 3, that's 10. Plus 12 is 22. And that'd be 26. Would this be 42? Did we add that right? Sarah, don't be tricking me. This would be 10, 26, 38, 42. And can we beat that? And see, some of us don't like problems like this. We didn't like it on logic problems. Can it be beaten? Is there a better way? You know, Mr. Nice, he doesn't even have a cell phone. Because, you know, he was fine with the phone being on the desk. And so, it doesn't matter. So his wife and him just share a phone. But sometimes we appreciate all of you who do look for a better way and try to get that. And so we have that. There is one problem on your homework that normally we want to do minimize the costs. But sometimes you want to maximize the cost. And there's an example. It's like, when would you want to maximize, make the most money, or have the most traffic? How could I maximize traffic between, if we do this, we'll get more customers. If we go this way, there's more people on this road. You know, these are the number of people on the roads. And so we want to put signs on certain ones or something. And so this one, you'd want to highlight if you were maximizing. You'd want to pick the big numbers. And so we can look at this. Or you can always Google, why would you want to maximize a minimal spanning tree? Or read the next problems. And so you'd want to connect. And then maybe you'd want to connect. and we'd want to make the maximum connection, the maximum connection, the maximum connection. And so that'd probably be a maximal spanning tree. And you can't just add in more to make a maximal spanning tree. Well, I'll just connect everything. No, you still don't want to duplicate roads. You only want to connect them once. And so that would probably be a maximal spanning tree. But normally we don't talk about those. This is what we want, a minimal spanning tree. Okay? And so the thing is, sometimes using our counting, like on the last homework we had permutations and how many ways to count. Well, the thing is, if we were just going to connect these vertices, how many ways could you do it? Well, is it 4 times 3 times 2 times 1? Is it 4 factorial? 24? Well, Mr. Nysen didn't give me 24 boxes. Well, we could go 1. We go 2. We go 3. We go 4. Well, what else could we do? 1, 2, 3, 4. Are there more? How else could we connect these? Or are there only 8? Then how would I go 24 divided by 3 is 8 and get that? And so if you're connecting, I could go to this one first. And then I could either go to this one or this one, which was this one or was this one. And for each of those corners 4, I would then have 3 choices. Oh, I forgot. Look. I could go here and then go here and then go here. I already got that one. What if I did 1, 2, 3, or 1, 2, 3? Oh, that one. There's some more. Oh, I forgot that. And so we could do like a little table. There'd be one like that. And then the table could sit on the bottom. I could go like that. Or the table could sit on this side, and then I could connect them like that. Well, then there's 4 more. Now I'm up to 4, 8, 12. Is there something else I forgot? Maybe we will just leave that for you. Is that all of them? Or is there more? What else could I do? And maybe we give you N plus if you can give me more. And just add it to your homework. And that shows me who is watching the whole video. Interesting. So, of course, computers and things help us with all this, because sometimes networks and things are very complicated. And to think about doing this by hand would become very difficult. Last problem on the notes, we have this larger network, and networks can be really, really large, and computers do most of this, and then you, as a math person, you program computers and you get all this stuff done. But on a larger network, we want to connect all of these terminals together, nodes, cities, vertices, whatever you want to call them, and we want to connect them. And so one way is just use the nearest neighbor. Like maybe these 2 towns are 28 miles apart and these towns are 7 miles apart, but going this way, it's only 1 mile apart. And so, you want to connect that one. And so you might want to connect, that's a 2, and then this is a 4. And look for the nearest neighbor, this would be a 5. And then to connect over here, we'd probably go with the 8. And then here to connect these, we'd go with the 12. And then this would be the 6. And to connect this vertice, we'd probably go this way. And then to connect these 3 up, we'd probably want this one. And so then how are we going to get these pieces connected together? Well, it'd be less if you connected those. Then how can I get this piece connected with these? Well, it'd be less if I went here. Then how can I connect this with this one? Well, we'd have to go here. And to connect those, we'd want to go to that one. Now we just have two pieces to connect. Well, the cheapest way would be to there. And so then not only do you need to show the path on your homework, you need to add these up. And don't forget any of the numbers. And I'll probably goof up and forget one. And so if you add all those numbers up, we would get 2 plus 4 is 6, 11, 19, 38, 55, 68, 86, 87, 94, 109, 115, 127, 143. And that's what all those, and it's divisible by 11. And so that would be the network for that. And so you just go to the nearest neighbor and then web out from there. So for your homework, the last one of 3 years, it's notes 132, sorry, and I didn't delete that. Notes 132. And so I have everything drawn for you, so even if you do have your textbook yet and you're like, I'm going to check the odd ones quick before I turn it in today, you can get these. Find the minimal spanning tree. And so show it, and then also tell me what it adds up to. Show it, tell me what it adds up to. And then it says, if a graph has n vertices, how many edges would you have to draw? The same amount, one less, one more, what would it be? Give an example of a maximal spanning tree. And then for part B, it says copy graph 1, but you don't have to because I already put it right here. And then it says talk about the maximal spanning tree like I hinted at on the notes. Number 5 says the graph at the right shows dollar cost to form a computer network. So you want to, this is 6 of them. And so you have 6 edges on a hexagon. And then you also have the diagonals. But in this one, it didn't draw in all the diagonals. It didn't draw that in. And so it doesn't have them all for some reason. We're not going to connect A with D. And so you only have to do what's given. But on this next problem, instead of giving you a picture, it gives you a table. It says the cost from A to B is 18. The cost from B to C is 10. The cost from D to B is 18. And so it says to draw a graph. Well, I would draw a hexagon. I would make it as big as you can and still fit it in here. A, B, C, D, E, F. And you have your vertices. Well, then label. A to B is 18. And label. B to C is 10. But then A to D is 30. And so a hexagon, you have your 6 edges. But then you also have all your diagonals. Jacob, how many diagonals does a hexagon have? Yes, n times n minus 3 over 2. So 6 times 3, 18 divided by 2, 9. 1, 2, 3, 4, 5, 6, 7, 8. Oh, there's the 9th one. CD. And so you have all these, and then you can label them. And you don't need them all. You just need to minimize the cost to connect the 6 ones. Which ones would they be? And then problem 7. We have, if I move this out of the way, a college wants to build sidewalks between these buildings. But then it says the president's home, between the president's home and the administration building is the most expensive one, but he wants a sidewalk because that's where he works and he likes to walk through campus every day. So if you have to use that, what would be the minimal spanning tree? And then if you did not have to use it, and you didn't have to listen to what the president says, but a president of a college or anything else, you have to listen to who's in charge. And so if you don't use that one, then what would it be? So you could try to draw 2. I should have copied it twice to show it, but sorry about that. But you can kind of just show the change in what they are. Okay? And when you get that done, you have finished 3 years of math assignments. And so we've really enjoyed having you in class. And so the computer, I already recorded this end once, and the computer didn't record it, and I was getting rather emotional. And so, but maybe that's why it couldn't handle no crying in math class, and so it couldn't handle that. But we've really enjoyed having all of you in class these past 3 years, 540 classes if we would have had class every day through this year. And so all of you have learned a ton, and we've really enjoyed having all of you in class. And so keep working hard. You're going to see how well prepared you are next year. And I know some of you are taking the SAT and the ACT over the summer, and you share those things with me. And so keep me updated on how things are going. Some of you have basketball and baseball and choir and things like that at the high school. So just email me and let me know and check in. And so maybe we'll try to make some of those things of your high school career. And so it's been a great 3 years. And so I'm getting emotional again, but we miss all of you. Great job, everybody. So proud to be your teacher. Great job. Bye-bye.